Let's talk about power in AC steady state. We begin this session with a review of RMS and effective values. But even before that, a parenthesis on power. How is it that we compute power in any electric element with two terminals? Easy. We multiply the voltage in the element and the current through it. And that applies to every element, even in a resistor. But in a resistor, we have Ohm's law that we can substitute in the formula PVI and write that if we know the current in the resistor, its power can be computed as RI squared. Or, if alternatively, we solve from the Ohm's law for the current and replace that in the power formula, the power in the resistor can be computed as V squared over R if we know the voltage in the resistor. I insist, if we know the current in the resistor, we can compute RI squared. We can compute V squared over R only if we know the voltage in the resistor. Those formulas work exclusively on the resistor. Why am I saying this? Because I've seen in exams that a few students, very few, fortunately, try to use these formulas on elements that are not resistors. Let's have some exercises. You see that current there, 3 amps, and the resistor 2 ohms? Tell me, can you use the RI squared formula to find the power in that resistor? Say the power is RI squared 18 watts? Of course not. Why not? Because that is not the current in that resistor. How about now? Can we compute RI squared as the power in that 2 ohms resistor? Yes, indeed, because that is the current in the 2 ohms resistor, 18 watts. What if we are given the voltage 3 volts? Can we use the formula V squared over R to find the power in the 2 ohm resistor? No. Those 3 volts are not the voltage across the 2 ohms resistor. But if instead we were asking what is the power in this other 2 ohms resistor, yes, there we could say the power is V squared over R, 3 squared over 2, 9 over 2, 4.5 watts, and that is fine. And that is a parenthesis. Now, let's talk about RMS values. The original Dartson Valley instruments read the average of the current flowing through them. They were electromechanical devices like this. We would put a coil around a cylinder of iron that could move in the middle of a magnetic field. Attached to that drum, there was a needle. The needle would move on a paper scale, and the displacement was proportional to the current that would pass through that coil surrounding the drum. If the current was changing slowly with time, the displacement of the needle would also change slowly with it. But when the oscillation of the current was too fast, the mechanical inertia of that iron drum would prevent it from following the current, and all you would get would be the average of the current. This was a mechanical way of finding the average of a current. They were very well suited for DC current measurements, but when AC currents entered the field, those instruments were reading the average of a sinusoid. A current like that. What is the average of a current like that? You know, 0. Those instruments were reading 0. Why? The average of a sinusoidal wave is 0 voltage or current, right? And that is because they are negative half of the time. So someone said, if we square them before we average them, we get a non-zero average, right? Let's square them before we average, and square them, find the average. And they actually found out an electromechanical device that could find the average of the square of the current. There was a problem. Now, we didn't have amps anymore. We had ampere squared, or volts squared. Easy, the inventors said. Just rip off the paper scale under the needle and substitute that with another where the numbers have been replaced by the square root of the original ones. That is, take the square root of the measured value, and then we have, again, amperes. What have we done? We have found the root of the average of the square of the original current. Another word in English for average is mean. We found the root mean square, or RMS value, of the function I of t. Recap, RMS. To find the RMS value of a function of time f of t that can be a voltage or a current, we square the function of time. We take the average over one period, I'm assuming it's periodic, and then we take the square root of it. The root mean square, that value. Does it have any physical meaning, the RMS value? Well, let's see. Let's define the effective value of a time-varying current or voltage. The effective value of the current I of t, written I sub EFF, is a DC current that heats up the same resistor by the same amount in the same time. Let's run this experiment. A bucket of water with a resistor that has been carefully insulated. We have also a thermometer and a chronometer. We run the current I of t through the resistor and let it run for a given time and check out how much the temperature went up. And then we repeat the experiment on a separate cool bucket with different values of DC current until we find a DC current value that heats up that resistor by the same amount in the same time. When we do, that DC current is the effective value of the original current I of t. Effective value, right? We have the same readings for time, the same readings for temperature rise, and then we say that IDC is the effective value of I of t. Is there any analytical way of determining that effective value instead? Oh, you bet there is, because heating is proportional to the average power dissipated, right? And for a DC current of value IDC, the power in the resistor R is just R, IDC squared. While for a time-varying current I of t, the average power in R is 1 over t integral of R I squared dt. If the DC current is the effective value of our original current, then both two powers have to be equal to one another. We can simplify for resistance, take the square roots, and find that the search for DC current is the root mean square of the current. That means that the effective value is another name for the RMS value. There's your physical interpretation of the RMS value. Effective value, RMS value. Summarizing, the effective value of a current is equal to its RMS value, like that. Effective value or RMS value of a sinusoidal function of time. For a sinusoidal current or voltage, like this one, with a peak value I peak, if we apply that definition, that formula for root mean square, we obtain that the RMS value, the effective value, is a peak value divided by root 2. That's how we find the effective value of a sinusoid, the peak value divided by root 2. From now on, then a sinusoidal current with a peak value A can be also written using its effective value A over root 2 this other way. Root 2 multiplied by the effective value M instead of the peak value A. AC ammeters read the RMS value of the current, and AC voltmeters read the RMS value of the voltage. In power systems, we always refer to RMS amps or RMS volts by default. If we hear that the voltage is 120 volts, we know they mean 120 volts RMS. If we hear that the current is 60 amps, we know they mean 60 amps RMS. When we go to the power outlet on the wall, and we know the voltage is 120, that 120 actually is the RMS value of the voltage there. It's a 60 Hz 120 volts RMS. If that voltage is sinusoidal and reaches up a peak, a maximum value of root 2 times 120, that is about 170 volts on the peak. In the laboratory, multimeters these days, they measure volts and amps. They measure volts and amps both in DC and in AC. If you set them up for DC, they read the average value of the voltage or the current. If you set them up for AC, they read, you guessed, the RMS value of the voltage or the current. Look, let's zoom in. The 4 buttons there set the multimeter to read DC volts, DC amps, or AC amps. Let's have some tutorial time. Let's imagine that we put that periodic current through a DC ammeter. And the question is, what is the reading? Well, you know, the reading is going to be the average value of that current. The period, 11. The average would be integrate that current between 0 and 11 and divide by 11. Sure. The first segment is 3.5t between 0 and 2. Then 7 between 2 and 5. Then 22 minus 3t between 5 and 8, and negative 2 between 8 and 11. Let's find that average. There you see the four integrals added together and divided by the period 11. That is the average, 2.68 amperes. And that is the reading that the DC ammeter will give you. That is not the effective value. The effective value is the RMS value. This is just the reading that a DC ammeter would give you for that current. Now, another tutorial time. Same current, different question. We put that current through an AC ammeter. What is the reading? Well, would be the RMS value of the curve. We find the integral of the square of the current between 0 and 2. Integrate from 0 to 2, the square of 3.5t. And then P2, the second segment, is integrate from 2 to 5, 7 squared. And the third one, integrate between 5 and 8, 22 minus 3t squared. And the last one, integrate from 8 to 11, negative 2 squared. We add them all four, divide by 11, and take the square root. And we get the RMS value of the curve, 4.6 amperes. That is the effective value of the curve. That is the RMS value of that current. Another tutorial time. What is, in general, for any sinusoidal current, the RMS value, the effective value? That current has a peak value and a frequency omega radians per second. The frequency in hertz would be omega divided by 2 pi. The period is the inverse of that frequency in hertz. The function itself, Ix, is I peak cosine of omega t. Let's find then the square root of the integral of Ix squared divided by the period. And look, the RMS value is just the peak value divided by root 2. An easy formula to remember. To find the RMS value of a sinusoidal function of time, divide the peak value by root 2. That allows us to write a sinusoidal function of time either expressing the peak value explicitly or the RMS value explicitly. The peak value is root 2 times IRMS. The IRMS is what the ammeter is going to read you in AC. Up to this point, we've been using peak-valued phasors. From this point on, following industry standards for power computations, we shall use RMS phasors exclusively. If this is the function of time written this way or that way, we can represent that with a peak-valued phasor the way we've done, or with an IEEE, an RMS phasor, that we shall do from now on. Tutorial time. For the following AC current, write it in such a way that the RMS value is explicit. We take the RMS value. How? Peak value, 75 divided by root 2, that would be 53 amps. And we write the same current with the same peak value, but the peak value, we write that as root 2 multiplied by 53 amps. What are the peak valued phasor and the IEEE phasors that represent that function of time? Well, the peak value phasor is just 75 with 67 degrees. And the IEEE phasor, the RMS phasor, is 53 amps with 67 degrees. Both of those phasors represent the same function of time, but they have different meaning. And it's time for us to take a break.